How do you measure something you can't see? Imagine trying to find the exact moment a sour lemonade is perfectly neutralized. Not too sour, not too basic, but perfectly balanced. You can't just look at it. What if you had a tool that could track that balance, drop by drop, with incredible precision? Well, in chemistry and engineering, we do. And today, you're going to master it. Welcome to our guide on pH-metric titrations. This is a powerful technique used everywhere, from making medicines to testing our drinking water. By the end of this video, you will understand, first, the core principle of pH-metry. Second, how to properly calibrate a pH meter, a crucial first step. Third, how to analyze the classic S-shaped titration curve for a strong acid and a strong base. And finally, how to find the exact equivalence point from your data like a pro. Let's get started. So, what exactly is pH-metry? Formally, it's a potentiometric method where the potential of a glass electrode, which is directly related to the solution's pH, is measured as a function of the volume of titrant added. Okay, let's break that down. Forget the jargon for a second. Think of a pH meter as a super-sensitive electronic tongue. It's not tasting for flavor, it's tasting for acidity or alkalinity. In a pH-metric titration, we use this electronic tongue to watch, in real time, how the acidity of a solution changes as we slowly neutralize it. We're essentially creating a play-by-play report of the chemical reaction. Imagine this setup. We have our acid in the beaker, and the pH meter shows a very low value, maybe around 1. Now we start adding a base, drop by drop. Watch the number on the pH meter. It starts to climb, slowly at first, 1.3, 1.7, 2.5. We are tracking the neutralization live. This isn't just a lab experiment. This is the gold standard for quality control in the pharmaceutical industry. When a company manufactures an acidic drug like aspirin, they use pH-metric titration to confirm its purity and concentration with absolute certainty. You can't use a simple color-changing indicator for that level of precision. Now, before we can trust our electronic tongue, we have to teach it what's what. This is called standardization or calibration, and it's the most important step. Calibration is the process of adjusting the pH meter's output to match known standard values, ensuring the accuracy of its measurements. Think about a digital weighing scale in your kitchen. Before you weigh your flour, you put an empty bowl on it and press the tare or 0 button, right? You're telling the scale, hey, this bowl's weight is our new 0. Calibrating a pH meter is the exact same idea. We use special liquids called buffers, which have a precise, stable pH that we know for a fact. We dip the meter in a buffer with a pH of exactly 7, and we tell the meter, this is what a perfect 7 feels like. Then we do it again with a buffer of pH 4. Now the meter has 2 reliable reference points. It's ready to give us accurate readings. It's a simple 3-step process. Step 1, you rinse the electrode with distilled water to clean it. Step 2, you dip it into the first buffer, let's say pH 7, and press calibrate. The meter adjusts itself. Step 3, you rinse it again and dip it into the second buffer, maybe pH 4, and press calibrate again. And that's it. Your instrument is now reliable. Forgetting this step is like trying to measure distance with a ruler that has no numbers. Your results will be meaningless. Every single time a pH meter is used in a professional setting, whether it's an environmental scientist testing the alkalinity of a lake or a technician in a food processing plant, it is calibrated first. It's a non-negotiable rule that guarantees the data is trustworthy. Okay, our meter is calibrated. We're running our titration, adding the base, NaOH, to our acid, HCl, and as we do this, we're plotting our data. This creates the famous titration curve. A titration curve is a graph where the pH of the solution is plotted on the vertical y-axis against the volume of the titrant added on the horizontal x-axis. This graph tells a story, the story of our sour lemonade. At the beginning, we have lots of acid, so the pH is low. As we add the base, the pH starts to rise, but very, very slowly. This is the bottom part of our S. The acid is fighting back, resisting the change. But then, something dramatic happens. We get close to the point of perfect neutralization, and suddenly, damn, even a single drop of base causes a massive vertical jump in the pH. The solution goes from acidic to basic almost instantly. This is the steep middle part of the S. After this jump, the solution is now basic. And as we keep adding more base, the pH once again starts to rise slowly. This forms the top part of the S. This slow, fast, slow change is what gives us the characteristic sigmoidal curve. Here it is. You can clearly see the three regions. The initial, flat buffer region where the pH changes slowly. The incredibly steep inflection region where the pH skyrockets. And the final, flat region where the solution is fully basic. The middle of that steep vertical jump, that's our treasure. That is the equivalence point. This curve is the result. The entire goal of the experiment is to generate this graph. By analyzing this shape, especially its steepest point, engineers can determine the exact concentration of an unknown substance. It's a visual confirmation that the reaction is complete and a roadmap to the answer. So, you've collected your data. You have a table of pH values and the corresponding volumes of NaOH added. How do you find the exact equivalence point? Let's walk through it. Problem. Given the following data from an HCl versus NaOH titration, determine the precise volume of NaOH required for neutralization. First, you can do a quick visual check. You plot pH on the y-axis and volume on the x-axis. You'll get your S-shaped curve. Then, you just eyeball it. Find the middle of the steepest vertical section and trace it down to the x-axis. Let's say it looks like it's around 25 milliliters. This is a good approximation, but in engineering, close enough isn't good enough. We need precision. To find the exact point, we use a little bit of calculus. Don't worry, it's easy. We're going to look at how fast the pH is changing. The pH changes fastest at exactly the equivalence point. This rate of change is called the first derivative. Step 1. Calculate the changes. We add 3 new columns to our cable. Delta pH, which is the change in pH between readings. Delta V, the change in volume. And finally, the most important column, the ratio of delta pH divided by delta V. This ratio represents the steepness of our graph at each point. Step 2. Plot the derivative. Now, we plot a new graph. On the y-axis, we plot our steepness ratio, delta pH over delta V. On the x-axis, we plot the average volume for each interval. Step 3. Find the peak. Look at what this new graph gives us. Instead of a long, steep section that's hard to judge, we get a single, undeniable, razor-sharp peak. The highest point of this peak corresponds to the point of maximum change. The volume on the x-axis directly below the top of this peak, that's your precise equivalence point. Let's say it's 24.9 milliliters. Now that is an answer you can rely on. So let's recap. 1. A pH-metric titration uses a pH meter to track the neutralization of an acid or base, giving us precise real-time data. 2. You must always calibrate your meter with standard buffers first. No calibration, no reliable data. 3. The data creates a classic S-shaped or sigmoidal curve. The equivalence point, where moles of acid equal moles of base, is the midpoint of the steep vertical section. And 4. For maximum accuracy, you plot the first derivative, delta pH over delta V, to transform that steep curve into a sharp peak, pinpointing the equivalence point with perfect clarity. This technique is essential for any field that requires precise chemical analysis, from developing new medicines to keeping our environment safe. If this video helped simplify pH-metric titrations for you, please hit that like button and subscribe for more core engineering concepts made simple. Have a question or want to see another topic covered? Let us know in the comments below. Thanks for watching.